kind of cool how we were able to lift that ball off of the table even though there wasn't a bottom to the cup. So how that works, okay, so we need to have some balance in this situation so that it doesn't roll up and out of the cup or roll back down and out of the cup again. So what kind of balance is required? Well, there is a normal force. Now this normal force is pointed at this angle, and so the faster I roll it, the normal force gets bigger. And so that's what's causing it to go in a circle, but I need to have it such that the component of the normal force pointing up is going to balance out that mg, and so then I don't get acceleration in my y direction. So let's kind of see what this free body diagram looks like here. So we have mg down, we have this normal force pointing this way. All right. So we have that normal force pointing this way, perpendicular to this surface where our angle was 70 to, or whatever it is, I don't know, whatever your angle is there, theta. And so this angle here is the same as this angle here. So if you measure that angle, you will get this value. So now we just need to resolve this into the components. So this one's adjacent, so n cosine of theta. This one is opposite, so n sine of theta. All right. So now we got some things to work on. So some of the forces in the y direction is going to be 0 because we don't want it rolling up or down the incline. This is just going to roll because it's a ball. So we have n cosine theta minus mg equals 0. Sum up the forces in the x direction, parallel to the radius direction, and you're going to get MAC. We're going to substitute in there omega squared times r because our goal is to figure out what is the omega required to make that work. So here I have n sine theta. Inward, radially inward is always our positive direction, equals m times omega squared times r. Now we have to get rid of some variables. So I'm going to go ahead, I'm going to solve this side for normal force so I can substitute in over here. mg divided by the cosine of theta. Substitute that in, so I have mg sine of theta divided by the cosine of theta equals m omega squared times r. The m's cancel for us. Sine over cosine becomes tangent, so I get g tan theta. Divide the r over and take the square root, and we get ourselves the omega. So depending on your theta value and your r of your cup, you should be able to calculate the omega needed to maintain to keep it from falling out of the cup. Now we do have to be careful on this one because let's think about some feedback in here. So like if I start going and I give it too much omega, so my omega gets larger. Okay, so as my omega gets larger, notice it's omega squared too. So as my omega gets larger, my normal force is going to get larger. And as my normal force gets larger, it's going to outpace that mg, and this is no longer going to be ma, or no longer 0, it's going to be ma. It's going to start to accelerate in my vertical direction. Mainly, this is the bigger number and it's positive, so it's going to accelerate up. Now, as we go up the cup, the radius is also getting bigger. Oh, so now the omega and the radius have gotten bigger. The normal force gets bigger. That increases the acceleration. So as we go up that cup, that radius is changing as well, and so it gets this feedback loop that it just accelerates faster and faster out of the top of the cup. And so if you see that happening, you're like, oh, slow down. Remember, the same thing happens if you try to get the acceleration to flip the other direction, is now it's going to accelerate down, and that radius is getting smaller as you go down, and so you run into the same problem. So you have to be kind of careful. You have to like time it just right so you have the correct omega value to keep it and maintain it. So give that a try for yourself.
All right, so the ball is in the cup. We're going to get it going around, and once we get it going fast enough, we should be able to lift it up off the ground. Oh, try that again. Get it going fast enough, we should see that it comes off the table, and then we can set it back down. Now the goal in reality would be to get it going fast enough so that you could carry it somewhere and then bring it back to that spot. I just have a hard time showing you guys this way and maintaining that spin. I'm a little better when I hold it over the top, but harder for the camera to see. There we go.